In this lesson, we're going to see how we can do simple operations with radicals. Now, radical is just a term that basically means working with the square root. So radicals, when you working with radicals, we'll be working with things that are under the square root symbol. So let's start with multiplying radicals. When we multiply radicals, things under the square root symbol, the values under the square root sign are multiplied together, and then we can take the square root of the new product that we got. So, as you can see in the first example, square root 25 times square root of 4. 4 times 25 is 100. That's the same as the square root of 100, which equals 10. You can see how it would give you the same answer even if I did them separately, because we know that the square root of 25 is 5, and the square root of 4 is 2, and 2 times 5 equals 10, so I would get the same answer either way. So it's just getting the same result as in a separate, different path, let's say. Sorry, that was supposed to be erased, just because we don't need that there. And you can see it's over there on the right as well. Square root of 36 times the square root of 9. 36 times 9 is 324. So square root 324. If I take the square root of 324, it equals 18. Just like the square root of 36 is 6, and the square root of 9 is 3, that would equal 18. So root 4 times root 16 would be 64. Square root of that is 8. Just like square root of 4 is 2, and the square root of 16 is 4. Again, likewise, we have the same answer in both cases. Now, not all square roots can be simplified. Obviously, if it's a perfect square, we can take the square root of it to get a whole number, but not all square roots are of perfect squares. So in that case, we can work with something called a mixed radical. A radical, again, it's called a mixed radical when part of the value is a whole number and the other part is a radical. In other words, something under square root symbol. So example, 2 root 3. That's a mixed radical. The whole number is 2, the radical is the root 3. Or 5 root 6. Whole number 5, radical root 6. So a radical is changed into a mixed radical by considering the factors of the value under the square root, where one of the factors includes a perfect square. The root of a perfect square is then stated along with the root of the other factors. So here's a couple of examples. 24, square root of 24. That's not a perfect square, so I can't just take the square root of it. What I can do is I can break it down into a perfect square, which is the root 4, times, again, something that's not a perfect square, the root 6. The square root of 4 is 2, and so that's where the 2 comes from, and the square root of 6 stays the same. So that would be 2 root 6. Root 72, again, that's not a perfect square, but I can break it down into root 36 times root 2, and root 36 is a perfect square. And so, therefore, when I take the square root of 36, it equals 6, and the root 2 is still there, so I'd read that as 6 root 2. 6 times root 2 is what that means. So a few other examples. Root 80. What I want to do is I want to think about what can I break that down into that's going to have one perfect square and one not that I can then take the square root of. Well, 16 goes into 80 5 times. So 16 times 5 is 80, but I know that the square root of 16 is 4, and I can just leave the root 5, and that would be 4 root 5. Notice how these numbers, the root 6, the root 2, the root 5, they can't be broken down any farther. It's like reducing fractions. I want to reduce my radicals as far as possible. So 6, 2, and 5, I can't break them down into any other smaller radicals. So I know I'm done at this point. But sometimes I might change something from a whole radical to a mixed radical using this method, and I might realize that what's under the square root sign is still big enough that it can be broken down a bit farther. Sometimes we're going to see mixed radicals that are, well, they're already mixed, this 5 root 27, but again, this 27 can be broken down farther. I can't take the square root of 27, but I can take the square root of 9, and 9 goes into 27. So normally I'm going to write it like this. I'm going to leave the 5 here. Instead of writing two separate radicals like I did here, I'll just write it as a single radical. So I'll write this as 9 times 3. So 9 is my perfect square. So when I take the square root of the 9 part, that equals 3. So actually, maybe I won't write it as a separate radical. Stick with what I had. So 5 times square root of 9 times 3, like that. Maybe that would be a bit more consistent. So when I take the square root of 9, I get 3. And I still have that root 3 going on. But of course, I can simplify things. There's no reason for me to leave 5 times 3 like this. We know that 5 times 3 is 15. So that would become 15 root 3. And so if I go back, I can always check what I'm doing too. If I do 5 times root 27, 5 times square root 27, that equals 25.98. Compare that to 15 times the square root of 3, which is what I got when I simplified it, and you can see I got the exact same answer. So they're equivalent, but I've reduced it to its lowest form here. And again, doing this one, -6 times perfect square. If I want to break 12 down into a perfect square, I'd do 4 times 3 because 4 is a perfect square. And so it's going to be -6 times 2, which is the square root of 4, and then times the root 3 again. And so that would become -12 root 3, and that would be my answer there. So again, the root 3 can't be broken down any farther. So that's how I know I'm done. Whereas this 12, this 27, even though there's numbers outside the radicals, they could be broken down farther, and so we keep going until we get to the end. We can add and subtract radicals in the same way that we would add and subtract like terms. But instead of having the variables, we're not looking for the same variables, we're looking for the same radicals. So I'm going to treat the root 2, in this case, as if it was a variable. So it's like I've got 3 root 2's and I'm adding 5 root 2's to it. Well, now I've got 8 root 2's, don't I? So 3 plus 5 equals 8. So if I want to find the perimeter of this shape in its simplest form, we know that perimeter is just adding all the sides together. So I might start by writing them all out. Root 12 plus 2 root 3 plus root 8 plus root 18. Now each one of these radicals, I'm going to try to simplify farther if possible. 12 could be broken down into root 4 times root 3, which when I do root 4, take the square root of root 4, I get 2. So 12 is the same as 2 root 3. 2 root 3 can't be broken down any farther, so I'll just leave that second term the way it is. Root 8 could be broken down into root 4 times root 2. Maybe a little highlighting would be helpful. So that's that term. There's this term, didn't do anything to that term. The root 8, I'm breaking down now into root 4 times root 2, but root 4 is just 2, so that'd be 2 root 2. And then the last one I'll highlight in orange, and I can break that down into root 9 times root 2, and the square root of 9 is 3, so it's 3 root 2, and again, that all came from the root 18 to begin with. Now, like terms, I've got a couple of root 3 terms, and I've got a couple of root 2 terms. So again, I can add together the like terms. So 2 root 3 plus 2 root 3 becomes 4 root 3. And 2 root 2 plus plus 3 root 2 equals 5 root 2's. That came together from the ones that I underlined in green. I can't go any farther because now it's like I've got unlike terms. I've got 4 root 3's and 5 root 2's, but they're not the same type of term, so I have to end it there. We can also, and this is the last thing we're going to do in this lesson, multiply binomial. Well, we can always multiply binomials together using FOIL, right? But when I multiply these radicals together, we're going to see that sometimes some simplification can be done as we go along. So we know for FOIL from our grade 10 multiplication of binomials, I would do first times first, outside times outside, inside times inside, and last times last. So when I do that, 3 times 2 is just equal to 6. That's my first term. Then when I do the outside times outside, I do negative root 6 times 24. So I'll just multiply that together and reduce it later. 6 times 24 is 120 times 4, 144. So remember we got this minus sign here. I'm doing the negative root 6 times 24. That's where this minus sign comes from, because negative times a positive. And now I'm going to I'm not doing the right order, am I? Let me backtrack for a second. I said I was going to do first times first, which I did. 3 times 2 is 6. But I should do, if I want to follow the correct order for FOIL, not that it matters in the long run, but if I want to do the correct order for FOIL, I should do 3 times root 24 next. 3 times root 24 is just 3 root 24. Now I'm going to do the negative 6 times the 2, and that would be negative 2 root 6 if I put the whole number out front. And then finally I get the negative 1 root 144. So I skipped ahead a bit, and sorry for going out of order there, but there's 4 multiplications. In the end, the order that I do them in doesn't matter, but that's the order that we would follow for FOIL. Now I'm going to simplify any radicals I can. Obviously 6 can't be simplified, but 24, the biggest perfect square that goes into 24 would be 4, right? 4 times 6, it gives me 24. And so I can, again, maybe some highlighting will help. And so this broke down into that, and then this negative 2 root 6. I can't break that down any further. Root 6 doesn't go any farther, so I'll just copy that one down again. And the 144 is actually a perfect square, right? It turns out that by multiplying 6 times 24, neither of which are perfect squares to begin with, I ended up with a perfect square, and so when I take the square root of 144, I get 12. And hopefully the highlighting is not throwing you off. It's just trying to show where things come from. But they're still, as far as gathering them together goes, I'm still just going to have, I'm still going to look for like terms. So maybe I won't highlight this next row here just so it doesn't add any confusion. But when I do square root of 4, that's 2. So this part here, square root of 4 is 2, and then multiplied by 3 is 6. So I'd get 6 root 6 from that, what started out as a green highlighting. Can't go any farther here, as we already saw. Can't go any farther here. So now I've gone as far as I can go as far as the simplifying goes, but I can collect like terms. So as far as like terms goes, I've got root 6 terms. So I've got 6 root 6 minus 2 root 6. So that gives me 4 root 6's, doesn't it? And as far as the constant term goes, I've got 6 minus 12, which gives me negative 6. And again, looking past the highlighting, that means the answer is 4 root 6 minus 6. So I'll just write it again, same answer, but again, I know that the highlighting, while it is, I think, useful for letting you see where things come from, it might sort of confuse the final answer. So this would be our final simplified answer here. And that's it. It's just some techniques that we can use for bringing radicals together and then simplifying them down. so that we can express them in the smallest, most compact way possible. In the same way that we always try to reduce fractions or anything else, we're always looking to simplify with math. So practice these. Let me know how you did.